Hello everyone. Today we will discuss the dynamics of a single degree of freedom system, and we will try to find together how to solve the equations of motion for such a system, first without damping and then when damping is added to it. Let's start by defining what a single degree of freedom system is. It's any dynamic system that can be described by the time variation of a single variable. For example, x of t, theta of t, angle of degree or temperature maybe, whatever, z, y, just a single variable. If you can describe everything in a system by the variation or the change in a single variable, then we can call that system a single degree of freedom system. Let's now recall the concept of stiffness. Stiffness basically can be defined simply as the resistance to deformation. Any elastic body when under load or stress, it deforms, it strains. Okay. Now let's focus on a spring. For example, the spring in the sketch in front of us now, whenever it's loaded by an extra weight, it elongates. That's deformation. The stiffer the spring, the less the deformation. That's why we usually define the stiffness of any spring as the resistance to deformation. Now actually we can generalize this for any system, not just vibrating or mechanical systems, such that whenever the change in the variable of a system is proportional to the change of is proportional to the externally applied excitation, we call the constant of proportionality a stiffness. Now let's zoom in and focus more on the dynamics of a mass that is connected to a stiffness. When this mass is moved from its original place, the stiffness tries to pull it back if it's elongating, and if the mass moves towards shortening the stiffness will try to push it away. So you'll find out that as x increases, the variable x here on our screen, here, as x changes in this direction, you will find that this stiffness will pull it back, as indicated by this part of the sketch. So this force will create acceleration on the mass, ignoring of course that there's any friction on this surface here. Okay, so now we can write the equation of motion using Newton's law. The mass times acceleration is equal to the summation of all forces. The only force that's acting in the horizontal direction with this on this mass is the stiffness, and the stiffness, as you can see, is multiplied by a negative number with x because it goes in the other direction. It goes opposite to the motion. So rearranging the terms, you come up with this equation of motion, which says that the mass times the acceleration plus the stiffness times the displacement is equal to 0. In this case, we say that it is equal to 0 because there is no externally applied force on our mass. However, if we decided that there is a force applied on the mass, then this 0 will change to f of t. Let's just indicate it like this, f of t, where f of t is a force, an excitation force applied on the system. We will get back to the excitation later, but for now we will solve the problem with just the initial conditions. Now we, for a second order differential equation like this one, we need two initial conditions, the displacement, say, and the velocity, in order to be able to solve the equations and find the time change of x of t. Now when we get to the solution, we start with the differential equation, mass times acceleration plus stiffness times displacement equals 0. The linear equation of this type has the general solution of a constant, here this constant, multiplied by an exponential. The general solution will be a constant multiplied by e to the power lambda t, where lambda is some variable we don't know. Now, differentiating this term twice and substituting back into the differential equation, we obtain the characteristic equation. This is what we call the characteristic equation. As you can notice here, A will fall from the problem because A can never be 0. If it's 0, of course, we have no solution. And e to the power lambda t can also be taken as a common factor, and generally speaking, e to the lambda t is not equal to 0 all the time. So we end up with the solution saying that lambda squared equals minus k over m, or that lambda is plus or minus j root k over m. J is the imaginary number, square root of minus 1. In many literature, we will find it written as j, and in other, it will find it written as I. So it's just to define that it's the square root of minus 1. That's all. Okay, anyway, so now we got two imaginary solutions for j. Two imaginary solutions for lambda. Using those solutions, again, mathematicians taught us that whenever you have more than one solution, then the general solution is adding both solutions. One is positive j root k over m, and the other is negative j root k over m. So we actually have two solutions. We add them. So instead of a single constant a, we end up with two constants, a1 and a2, multiplied by the exponential e to the power j root k over m t and minus j root k over m t. Let's define the variable root k over m to be equal to omega. Omega is a constant or a number that's defined only by the natural properties of the dynamic system. That's why we call it the natural frequency. This natural frequency can be plugged back into the general solution to get this x of t equals a1 e to the power j omega t plus a2 e to the power minus j omega t. Now we have a solution for the problem. This is the solution for the dynamic equation. Of course, a1 and a2 are constants that are going to be determined by the initial conditions.